Hello, and you're here with data science teacher Brandon, and we're going to go over the Space Titanic dataset. It's going to be a two-part dataset or two-part guided project. In the first one, we're going to do the data analysis, really with the intention of helping a machine learning scientist get ready and identify the things that he would need to build a good machine learning model. And I think it's really good. We're also going to focus a lot on the use of functions because we're going to be sharing our document. So we want it to be neat and clean and help the data scientist perform his job. Okay. So the links to the data sets, this is going to be, if you want to participate in the second part, this is going to be to submit a kaggle competition, which is why I expanded the analysis to spend some time on it and really try and do our best for the machine learning competition. Okay, so getting started, we have all of our standard data analysis libraries. Here are the machine learning libraries that we'll use in the next class, but we're not going to touch those today. So we'll just import our data, and here we go. Okay, so we're going to just do a quick .info. We can see, so we have passenger ID, home, cryo, sleep, cabin, destination, age, VIP, room service, food court, shopping mall, and spa. I'm assuming those are the amount of times they went to each one of those amenities in the spaceship that they're on. Okay, and the name and whether they are transported, true or false. So this is our target and transported, so they were able to be saved from the Titanic. They were transported, just like Star Trek, they were transported to safety. Okay, so that's what we're going to be focusing on for our target. You can see that it's a bool, so it's true and false. Were they saved or were they not saved? Okay, so starting off, always a good idea to understand your null value. So df.isNull.sum. Okay, so as you maybe have taken some of my guided projects before, you all know that I like nice pretty graphics. So here what we're going to do is we're going to import matplotlib, and then we're going to do is go matplotlib dot style dot use, and we're going to use BHM. One of my, I don't know, I just think it has a nice little feel to it, so I think it's a good data set to try for today. Okay. And so this does a lot of the formatting for the background, the kind of lots of little details of your plots, whether you use seaborn or you use pandas. It's more necessary with pandas plotting, but it creates a little bit extra texture, a little bit uniqueness to your plottings. I still like to add a little bit of color. So here I'm going to define a palette of different colors. And what I would do is I would go to colormind.io, and I just kind of go around until I find a palette that I like, copy these colors, and then put it in our palette right here. Okay, so that's how I usually do it and get started. So you can be a little bit different, but we have our palette and all the colors go together. So we don't need to really think about this again. We can just use those colors and we can change one or two if we're not liking how the colors are doing. To have a little bit of fun with the colors today, we made a little function. So we're going to define def r underscore color, so random color. We're going to set the number of colors by default to 2, and we're going to set the seed to none by default. So if the seed is equal to none, what we're going to do is we're going to go numpy dot, we're going to set seed equal to numpy dot random. So if we didn't give this a seed value, we're going to set one randomly, dot rand int. And this goes from the low of 0 to the high of 420, and I just want to return a size of 1. Okay, what this is going to do is going to set the seed, right? This is now going to set the seed randomly, but now I'll have access to what the value is, and if I want to, I can print it now. So I'll go seed np.random.seed. So I'm setting the random seed so I can control it if I want to, and I'm going to print out that seed value though, so I can see it and I can know if I like the random colors, if they look good, and do that again. I'm going to return from this is a list comprehension. So you can see this is in square brackets right here. You go pal I, so I'm going to take randomly I for I in numpy.random.rand int, so random integer from 0 to 5, not including 5. So we have 0 to 4, which is number of items we have here. We have 5 items. And I want to return a size equal to the number of the values that I give it. Right? So I'm setting this is just setting the random state, and then I'm returning a list comprehension. Okay, and this, and I'll be able to randomly return a couple colors from my palette, and we'll blend them with fun and have some fun with our plotting today. And I'll show you how we can control the random state. If we find a color palette that we like, we can kind of stick with that. So what we're going to do is we're going to create some functions. So define count underscore plots, our own count plot, because we had a lot of objects today, so we have a lot of count plots to use today. So we're going to go plt.figure, and all we're going to do is set the fig size, and then their next functions will automatically place, seaborn will automatically place its plot in this figure, right? So it's a nice easy way to set the size of your figure. It's really the only way with seaborn. Okay, so here what we're going to do is SNS, so seaborn dot count plot, and we're going to give it data equals df, x equals the column that we'll be passing this function. Our palette is equal to our color num and the seed. So if we give it a seed of none, then it will just generate a random, this random color. If we give it a number, it will generate that many random colors for our palette, and our palette will kind of organically adapt to the number of colors we need. Okay, so after we do the count plot, we're going to go plt.title, we're going to go plt.ylabel. So we're going to set the Y label. We're going to set the title to be automatically changing based on the column we give it. Y label will set our X label equal to column, and we're going to go plot.show. At the end, I found, so this is what I did at first. When I started working on it, I thought it would actually be good to see the value. So here we're going to actually return as well value underscore counts, just to get the actual values, just in case it would be nice to see them, sort of thing. Okay. And we're going to return that. So this is a quick little compact little function. And now when we go here, all we need to see is this one line of code. So this is especially beneficial if you're going to share this document, because now they're not looking at this copied and pasted 20 times for each plot. You're only looking at this one little line of code. It's much nice and neat and clean. And so what I need to do is define the palette first. And here, so just actually, I'm going to take out the random seed right here. So I set seed equal to 222. So what I did when I was first building this workbook, I would go through and I'd see here we're printing out the seed. And I don't really like this. Let me run this again. And okay, actually that looks pretty good. So I'm going to set my seed equal to 242. And now every time I run this plot, I'm going to get the same color palette. So it's a good way to kind of experiment with them, and then just, if you see one you like, you can then continue to use that over and over again instead of you trying to manually choose. I'm not an artist, so random chances is just as good as me choosing the colors. And here we go. We got a good palette here. I think this looks quite nice. And going through there. Okay, so we're going to go cryo seed. I set the seed for this one as well. Kind of the first time I was looking through it. In the cabin here, if we notice cabin, so cabin was a little bit tricky to get started. So we notice there's a zone, there's a seat, and a code. So it's a 3-part section. So really, it's not really super valuable to inspect in this format. So what we do is we have to separate a little bit. First, what we need to do is we need to fill all the null values in cabin. So fill the null values, and then we're going to go string dot split. We're going to split it on these values right here that we're separating the zones. So we're going to separate this. It's going to become a list then of zone, comma, seat, comma, code. And so this will allow us to access each individual one. So it's going to be a 2-step one. And so here what we can see, I just wanted to check after we look at this. So now we can see we have the list of those 3 values. And here we're going to go is null. And I just want to make sure that there are no null values. What we have to do then is a second step. So we're going to create 2 new functions, one for get cabin and one for get code, so that we can get the cabin, which is the zone, the first zone in this, and then the code being the last one. I didn't really think the seat number was super important, although you can inspect that as well if you choose to. Okay. So here what we're going to do is we're going to define get cabin. We're going to pass it x. We're going to use it with the dot apply function. So x is going to be the value in the row at each time. And then we're going to pass it. Apply is going to pass it to get cabin. So we can go if type x is equal to a float, then return numpy equals nan. So we're going to return a null value if it's a null value, because there are some that are null values. Okay, we're going to go else if length is greater than 1, right? So it's not just one value, it's a list. It's this list because there are some values. What I found is that there's only one value in there. So we had to make this conditional statement for that. So if it's more than 1, what we're going to do is we're going to return x equals 0, else return x. And then I just wanted to get it, it's just one value, but I wanted to get it out of the list. And so here we're going to return x equals 1. Okay, so we'll run this, run it on the function, and we'll be able to see count plot. Now we have our cabin zones. So now we can actually inspect the different zones of the cabin, extracting all of these from this. We can see here a little bit of an imbalance, especially in the zones, but we have now an ability to reduce this. And there's some notes that I wrote here, imbalance data set, and there's a potential to reduce these really small ones. So we're starting off by looking at just univariate. I should explain this, I apologize. We're using a univariate analysis. We're going to head into bivariate analysis, where we're looking at this in context of the target value. So this will be, we're doing a machine learning data analysis. We're getting stuff ready for machine learning. So we want to help the machine learning scientist, and they're going to be focused on the target the most. That's what we're going to focus on when we do our bivariate analysis. So doing the same thing here, we're going to do get code. So we're going to go if type of x, the value that we'll be passing our function every time. So if type x is equal to float, return none. Else if len of the x is greater than 1, return the third position, so x2, else return just the value by itself. It'll be a list of 1. Okay, so we'll return that, apply that, and then take a look at our count plot. Okay, and we see that we have the O cabin has very few people. We have a roughly balancing between the other two. And so this gives a potential for a reduction in the dimension. Is then, do we really need such a small occurring value? It might be better just to group with P or S, and we'll figure that as we go through our next step when we're looking at the target variable. Okay, so doing the same thing, we see here count plot, and we can see a very imbalanced data set. Lots of them are going to Trappist, a few are going to Canry, and PSO is very, very small. So maybe there is a potential for feature reduction, dimension reduction. And by dimension reduction, likely what we would do is create one hot dummy, so a new column of ones and zeros for Trappist, POS, and Cancri. What's going to happen with this is if we get rid of one of these, we're going to have less dimensions, less columns. So that's why I call it dimension reduction. Okay. So let's define another function here. We're going to do a hist plot, plt.figure, sns.histplot, plt.title, and we're going to organically put in the column title here each time. So run this function, and then we'll look at age. So the hist plot of age. Okay. So you can see here what I say is treating outliers. So just making highlighting this what I thought would be a good idea to do here is there are some very extreme outliers. And because outliers pull an average towards it, you can think of it in simple linear regression. A column is, everything in a column is going to be times by a coefficient, and the next column times by a coefficient, and all of those added together. If you can think of the coefficient, the best coefficient that it finds, it's kind of like the average best coefficient. I said average there for a reason. If the average is pulled towards the outliers, the average best coefficient across all of the rows is going to also be pulled towards the outliers. What works well for the outliers might not work well for the rest of the data set. So we generally, it's super surprising how much outliers affect our machine learning model, but we have to deal with this in some way. And so we wanted to mention here treat outliers. Plotting the BIP, so you can see very imbalanced data set. And so we'd have to decide if we even really want to use something that where most of the citizens don't even make, aren't really considered in this. Okay, room service is just like this. This is a hist plot again. You can see, so we have some outliers on the right hand side. You can't really see these, and this can be the kind of deceiving part. It goes out to 14,000, but it goes out to there, right? Even though you can't see anything, our human eyes aren't good enough. We can see there's a little maybe hint of something right here. but then there's just too few to really see here. But it goes up to here. So we know there's outliers over here, even though we can't see. It might only be one, it might be two, probably only one, but they go out to here. So we know there's outliers. And that was something very extreme, and we need to deal with those in some way. Okay. Looking at food court next. And the same thing here. So you can see a little bit of distribution right here, but it does go out all the way to 30,000. And so there is some values out here. We would need to deal with those. So outliers again on the right hand side. Okay. And looking at shopping mall. And here we see down into the right again, going down into the right. And again, it's coming out to here, 2,000. And I'm taking shopping mall, food court is kind of the number of times they went, or it could also be the amount spent in each place. And so some people, one, two, or three of the people spent a very large amount there, but the bulk of people spent a very small amount. Okay. And we want to make sure that we're predicting for the majority of the people on the spaceship Titanic, not for just the very few people that had $20,000 at the spa. This might be special circumstances, so we want to really make sure that our model is not adapting to outliers like we have, like outliers would make it do. So again, we're seeing the same thing here. It's a little bit of an exponential distribution where it starts at the top left and goes down into the right, but we know there are outliers here, and we know that outliers are bad for machine learning models. So again, just highlighting this, and that we want to be able to do something with these. And I put these all in these notes down kind of at the bottom. Okay. So now what we're going to do is we're going to find a displot to do a bivariate inspection. Okay, so this is a little bit complicated. We're going to do a few things in here. Okay, so the first thing that we're going to do is we're going to create a temporary data frame 1. So we're going to create 3 temporary data frames in here. And so what we're going to do is we're going to first go pd.dataframe. In the first one, what we're going to do is we're going to do the value counts of that, and that's going to give us a count of each value, with the index being the value of whatever column we're given, right? So if this is an object, it's going to separate by that. And what we're going to then do is we're going to divide by the sum of all of the value counts. And so we're going to do the value count. So we're not including null values for the specific value. So we're just going to divide it by the total number of values that they have. And so that's what we're dividing by sum of the value counts as well. Okay, so this is going to divide the total, each value by the total value. So kind of good to understand the starting position of what proportion each one of these made. So we're going to do another data frame then. And we're going to go transported equals to, logic statement, 2 equal signs, equals true, so 1. And then what we're going to do is we're going to select the column after we do that. So we're going to filter logic indexing, filtering only by when it's true, when they did get transported. And then we're going to select the column. Then we're going to do the value counts just on that column. So the same thing as above, we just added a logic statement before this. We're going to do the same thing here, divided by the sum of the total number that didn't, and then do the value counts on the columns, so that we are making sure not to include any null values when we do this value counts. So you're going to get the proportion of total and then the proportion of transported to each value of the total transported for this particular column. So that's good. So we have a comparison of how it was originally and then what proportion was transported from the total. So it gives us, if we're looking at the difference of who was there, the proportions to start with, and the proportions of who was transported, that might be insightful to understand which ones are important in our machine learning model, and maybe gives us some ideas on how to do feature engineering. Okay, so here what we're going to do is for data frame 3, we're going to go temporary data frame 2 minus temporary, df underscore temp 1. So I'm going to write df underscore temp 2. So we're going to go with the second one minus the first one. Then what we're going to do is we're going to stick all those data frames together. We're going to make one big data frame. So we'll go pd.dataframe, and then we'll go size equals to 1. Okay. So we're going to concat the data frames together, and we're going to stick them together vertically. Or horizontally. We're going to stick them size access equals 1. So we're going to stick them together horizontally and stick them together this way. Okay, because they all have the same index because we did that by the value counts, which makes the index. We're then going to change the column names. So the column, this is why we do this in function, because it would be a lot if we had to do this each time, right? So we're going to change the columns. We're going to set it equal to a list of the starting values, the transported values, and then the difference. So I know it's always going to be these three columns. So we're just going to replace those columns. We're going to organically set it with the column name that we're giving to our data sets. Okay, in the first one here, we're going to do a dis, dis plot, and it's dis, not dist. I just noticed it doesn't have the T there. This is one that is based, dis plot is based on facet grid and allows us to do something special. Here we're going to go data equals df, x equals column like we've seen here, and col equals transported. So we're going to have two side-by-side plots for transport, so we'll be able to compare them side by side. We're going to set our color equal to one random color, and we're going to index out of the list to get the actual value, and we're going to set the bins equal to 30. Okay, and then we're going to show this plot, plt.show, kind of like the print function for plot. We're then going to look at what I thought would be interesting, and I didn't do this originally when I set this up, so this is something to note that I built this one time, and then I came back and I wanted to get more of my plot for all of these. I was going to use this again all the time, so I added to this function. And here what I thought would be really cool is doing a his plot of the differences from this new reduced data frame that we create, just looking at the differences to try and highlight and see really where things were different. So we're going to say color equal to random color, and then our bins equals to 30 again. Then plot the title of plt.title. We'll set the difference in proportion organic with the column titles, and then we'll do plt.show. Okay. And I'm just noticing, this is kind of a good thing to point out. You can see the squiggly lines right here. It's good to just check before I run that. I ran that and I could see the squiggly lines here. So I noticed something was maybe a little bit off. It was letting me know that there was an error. It hadn't seen that variable before. So I probably had a spelling mistake. And I went and checked and it did have a spelling mistake. So it's good. I really like Colab because it helps you with your coding. It makes it a little bit faster and easier like that. And so now we have our function. So let's use our function for the first time and see what it looks like. Just noticing here with my error here, we had to pd.dataframe. I need to do pd.concat. And you can see my note here, concat the data frame. So df final is equal to pd.concat temp axis 3 and stuff. So just noticing that. Got inspected word access is because the data frame was equal to that. So just doing that. So we'll rerun the function again and take a look at this. And I got to, this is the function I had. We're not using a dis underscore plot, we're using a dis plot. Okay. So this is when you're experimenting with a new function that you just built, you get a couple things incorrect. And that's pretty common to. Okay, and you see we're getting another error here. Difference isn't there, so it's a little bit weird. I went up in here and inspected that we're changing the column name right here. So we're changing the column names, and difference I see it's right here, so it should be there. I'm just noticing right here when you see column, it should be the attribute is dataframe.columns, not dataframe.column. So it wasn't getting changed properly, and that was where the error was coming from when I did that. Okay. And so here we'll run our plot. Now you can see we get random different colors and we have a data frame of the difference. I think it's really important to understand the difference of Earth. You know, at the start they had 54, but only 45% of the people that were from Earth that were from Earth transported. So the proportion dropped by a very significant portion versus Europa. It was only 25 to start, but as a total proportion, but then 32 of the transported people got a 32%. See, there's a 7% difference, almost 8% difference. And I'm noting this down here as something that could be really helpful in our machine learning models. Okay, so doing the same thing, let's look at cabin code and cabin zone. Okay, so you see here we have those two right here. And we'll notice here that B has a big difference right here. We see B and C show some sort of differences. The rest almost show non-existent differences, and really G, A, 0, and T show almost no change. So this could be, maybe we combine those into the same dimension because there's no really value in terms of our target in having those separated. That's a theory, and that could be something that we test. Again, nothing is set in stone, so we could try that and find out actually it does help our model having those separated. So we want to create a theory and we want to experiment with that when we're doing our machine learning model. It's kind of experimental science. We have a theory and we want to test it. So this is a good way to start developing those theories, and this is what we're writing here. So we see this as well. We see that really because PC or PSO is really small, I made the note here, maybe we can just do, because there's really no change in PSO. So maybe we group this together some way, or maybe we just don't include this dummy because it doesn't really seem that it's really just absolutely no value in terms of our target. So the next one here, look at age. Okay, and so here, plot, we can see here, we see most of the differences are roughly about the same. There's not a huge change in the difference based on person, but we can see one time it happens a lot more. There's a big change, 1% more for this group, but this is right here for the age 0. There's a bigger change than really any other value for this. And you can see the biggest negative value is almost 1%, 0.007. So 0.7 of a percent. So a little bit here as well. But I think the biggest one is for children of the age 0, babies got saved a lot more often than everyone else. So you can see the proportion went up from 2% to 3.3%. So a big jump, an extra 50% of those children were saved. And so one thing else I noticed here is that over the age of 60, we have a lot of null values here. So you can see that there's null value right here. Really, it's showing that really a big portion of anyone over the age of 60, I shouldn't say null values, but very, very small values, not even like a fraction of a percent. So really over the age of 60, there really seemed to be no difference in who it was. So that could be maybe we create one dimension just for everyone over the age of 60, because it didn't really affect if you were older, it didn't really affect you on your life. So here now looking at room service versus transported. Okay, and we'll look at this. So we can see here that there are some outliers. You can't really tell, but remember what we talked about above? We know that this goes out here. So even though we can't see something, we know that there is one difference is about 17%. That's quite massive. So again, this happens for people that used room service 0 times had a 17% better chance of being saved. I think that's never going to use room service again. It's very, very interesting noticing that, right? Because that was very valuable for machine learning because that really will affect our target. So doing the same thing here for food court. This is the number of times people have used a food court. We see we do have some very large outliers here as well that we notice up above. And really there isn't a big difference between either one, the transport or true or false. And look at the combined one, we see basically almost everyone has a very, very small difference, but there is a very small amount, maybe just one time, that happens over 10% difference, which is really interesting. Most of the time, it's really not affected at all. But when the person used the food court 0 times, you can see they have 11% better chance of surviving. Very interesting. So learning lots of things that will be very valuable for a data scientist in helping our data science build his machine learning models. Okay, so here we're doing the same thing here, looking at differences. We look at those, look pretty standard by itself, but looking at the difference between them, we can see that sometimes things generally hurt your chances, but for the most part, there's only one time, or I would assume there's only one time where the distribution goes above 12%. And this is again, if you use this shopping market 0 times. It's interesting that if you didn't use any of the amenities, you had a better chance of getting saved. So here we're seeing that. We can see for the most part, everything else, using it any amount of times, gave you a slightly worse chance of being saved. Okay, so looking at SPA next. And we can see here, again, 0 being used, you get 17% chance better being saved if you did not use the SPA. It's very interesting. The boring people got saved more. Let's take a look at the VR deck. Okay, it's the same thing here. Again, we're seeing that not using the VR deck, for whatever reason, is very valuable in being saved. And so here, again, a 16% better chance of being saved. And what I did just to get ready for the machine learning science, I copied and pasted all of these, just the observations that I took underneath each one of these. So where's my observations? So here, I just copied and pasted those down and put them all here so we can look at each one of these and really just have a summary for the machine learning. I highlighted, things that would be valuable in pre-processing. I think one of the interesting things that we'll play with when we get to the machine learning side of this is the feature crosses of 0 visits for multiple amenities. So if they didn't use the VR and they didn't use the spot, they have a much better chance of being saved, or is it just the boring people that didn't use anything had a better chance of being saved? So we may be able to highlight this, something that we just learned in our machine learning model, because our model would not know that 2 columns are related unless we give it another column signifying that those are, when they both occur, true. This one is also true. So it could be really, really interesting, some of the things we learned, and really helpful in building our machine learning models. So thank you very much for joining me, and I will see you next time for the machine learning version of this, or the machine learning part of this data set. So thank you very much for joining me.